Hello, I'm Dr. Abhishek Sharma. In this video, I will discuss pulse code modulation. So let us start pulse code modulation. Pulse code modulation is a method that is used to convert an analog signal into its digital equivalent. Basically, pulse code modulation is a baseband digital transmission technique where baseband belongs to the low frequency analog equivalent digital data. Modified analog signals can be transmitted through the digital communication network with the help of PCM. PCM is a binary form, so there will be only two possible states like high or low. High will be represented as 1 and low will be 0. Now we can also get back our analog signal with the help of the demodulation process. Pulse code modulation process is done in 3 steps. Number 1 is sampling, quantization and encoding. You can clearly see that sampling is the first process, after that quantization and then encoding. Number 3 steps. So pulse code modulation process is done in 3 steps. Number 1 is sampling, quantization and encoding. So this is very important. This is digital encoding. This is a digital encoding technique where digital binary encoders are used which transmit decimal data to equivalent binary digits. Sampler is a device which performs sampling. That means in the sampling process there is a circuit called sampler which converts an analog signal into its equivalent sampled value. Now, point to be noted, for this sampling process there should be a upper frequency content which is required to identify the exact required sampling frequency. For example, as we know that according to the low pass sampling frequency, any band limited frequency having maximum frequency content FM can be recovered from the knowledge of its sample values taken at a rate of twice of FM samples per second. This twice FM is the minimum required sampling rate. So point to be noted, this is the sampling rate. That means this is the sampling frequency, right? This sampling frequency is very much important because twice of FM is considered as Nyquist frequency, as I have already told you in the previous videos. So we have to sample our signal with the rate of twice of FM, where FM is the maximum frequency content of our message. Right? So this is the ideal sampling performed by the sampler. You can clearly see that these are the you can say discontinuous discrete sample values of the above signal. This process has been already discussed in the previous videos. Now message signal is sampled with a train of impulses, right? So this is an ideal sampling. So we have done the ideal sampling in the sampling process. Sampling rate must be higher than the twice of the highest frequency content, which is the FM. So this is just nothing but twice of FM is the required sampling rate of the required sampling message sampling, right, for preventing aliasing. Aliasing is a phenomenon in which when this signal is sampled with a rate less than twice of FM, then the interference occurs with the coexisting, right, you can say, spectrum values. In practice, anti-aliasing filter is used at the front end of the sampler to reject higher frequency component higher than FM hertz to band limit the signal. So once I am talking about the sampling, so it is nothing but an anti-aliasing filter. Anti-aliasing filter is just installed. This is called anti-aliasing filter, which is required before the sampling process, because actually it removes any higher frequency component or noise values of higher frequencies which is not required as per the process. Now come to the next section of the PCM modulation technique, which is the quantization. So quantization process being performed by the quantizer. So quantizer sample values of analog signal and then pass to a quantizer these sample values, right? For example, these are the different sampled values. So let us suppose this value is 0.1, let us suppose. So this passes to quantizer, and the quantizer converts it into equivalent digital or decimal values, right? Whatever be the coding related to that quantizer. So quantizer represents the analog samples by a finite set of levels. These levels are nothing but decimal values. Like for example, if I have to feed the encoder, you can say the digital encoder, which is converting your analog decimal values to its equivalent digital. So we have to provide decimal values, decimal integer values to that encoder. So this process is called quantization process. The quantization is done by approximating the amplitude of each sample value to the nearest value from a set of predetermined discrete amplitude values. For example, if you know that there is a function in maths which is called as greatest integer function, so when you apply, like for example 1.2 in the greatest integer function, you will get 1. Similarly for 1.3 you will get definitely 1, 1.4 you will definitely get 1, and so on. So similarly least integer function will be 1.2 will be considered as 2, and so on. So the point is, from range over greater than, for example, if signal is greater than 1, let us suppose x of t, and less than 2, then it will be quantized to 1 if I am considering the greatest integer function for our quantizer, let us suppose. So now there are two types of quantization process. Number one is uniform quantization. Number one is uniform, and another quantization is non-uniform quantization. Non-uniform quantization, right? Two different uniform quantization techniques, or you can say uniform quantizers having output characteristic curve, right? So this is called mid-thread and this is called mid-rise. You can clearly see that between the mid values, this value is going up, so that's why it is called as mid-rise, and this is mid-thread. Now this is a simple process. With the help of this pictorial presentation, you can clearly understand how the quantization and encoding processes is relevant to the PCM. Now in this figure you can clearly see that all the voltage values which is less than 0 but greater than -1, like for example in this picture you can clearly see that from 0 to -1, right? From 0 to -1. Please note that in this figure from 0 value to -1, you can clearly see that this is the quantized voltage value. So that means if I am providing the input from 0, the range is between -1 to 0, I will quantize, or quantizer will provide it as output value -0.5. So this is very simple. So you can clearly see that this is V out and V in relation. You can clearly see that -1 to 0 range, the output will belongs to exactly equal to -0.5. Similarly from 0 to 1, from 0 to 1 range, you will find that the quantized value is 0.5. So it is from 0 to 1, from this voltage range to this one, you will clearly see that 0.5 plus 0.5 is the quantized, or you can say quantization level. So you can clearly see that how this curve is associated with this output, or you can say our quantizer is having the same input output characteristic curve, and we are performing the quantization as well as encoding process. Now in quantization process, after the quantization level has been find out or identified, the encoding process will be done, right? For example, -3.5, let us suppose the minimum quantization level, so I have considered this 0, -2.5 is being considered as 1, and so you can clearly see that as the quantization level going towards the higher value, this is 3.5, so the higher quantization level is 7. So 0, 1, 2, 3, 4, 5, 6, 7, these are the 8 coded values. So you can clearly see that this number of this is actually, you can say, the number of decimal values, right? Number of decimal values are 8, total 8. Now I am using 3 bits to represent, this is the minimum required bits to represent 8 decimal values, like 2 to the power 3 is equal to 8. So I have to clearly identify the required number of binary bits for a encoding process. Like for example, if 16 total 16 levels are required, quantization levels is already given, then you need 4 bits, at least 4 bits to encode properly. right? For example, you can clearly see that our sampled value is 0.25 in negative. So I'm going to clear this with the help of the eraser. Okay, then then you can clearly see this is the value which is minus 0.25, which lies between the 0 and minus 1. So the quantized value will be 0.5. That means I am encoding 3. So minus 0.5 is the quantized value and 3 is the code number, right? So binary equivalent of 3 will be 0, 1, 1. Similarly, for example, the another ideal sample is this value, which is 3.1. Now 3.1 lies between the 2.5, or you can say 3 and 4. So that means between the whatever the value between 3 and 4, it will be quantized to 3.5, which equivalent value is 7. So 3.7 is our quantized value and 7 is our code. So equivalent binary value of 7 is 111. Like similarly, this value is 1.5 and 1.5 will be quantized as 1.5 because it is exactly equal to the quantizing level. So the 1.5 is the number 5. So 5 will be decoded as 101 and so on. So this is the simple quantization encoding process with the pictorial presentation. While converting the analog signal with the help of the quantizer, there is a very important phenomena which has been happening. Like for example, if we are equating, like for example, this is the curve, right? This is the curve, this is a signal having a time varying signal, right? So the amplitude levels are different. Now let us suppose these two values, like for example, it will be clearly understandable with the help of this figure. For example, from this value, from these range, right? For example, there are several values, or you can say infinite values of between these two time instant, like 1 and t1 and t2, like these are the points. But these all values are quantized towards 3, and all these values are having equivalent binary code, which is 011. Now when you receive this 011, you cannot identify whatever was the transmitted value. Like for example, minus 0.25 having 3, you can say minus 0.27 is already having the same value, minus 0.3, or you can not 0.3, that means I will tell you, let us suppose 0.25. 0.25 will also have the same binary code. So you cannot clearly identify what was the transmitted value according to this binary code, which is 011. So this is the quantization noise, right? So in uniform quantization, original continuous time function is first rounded off. That rounded off means, like for example, you are just rounding between all the values between you can say 0 to 1 or minus 1 to 0. From this picture you can clearly see that towards the level minus 0.5, which is 3, right? So this is the round off process to several possible levels, now yielding a staircase type of waveform, right? This introduces an error known as quantization noise. This is the pictorial presentation of quantization noise. You can clearly see that this is the actual signal, but the quantized value is this one. So this is the difference between the actual quantized value and the actual signal value. So you can clearly say that at this point, as the signal is higher, so at this voltage is going towards high side and so on. So this is the true signal is represented in blue, quantized signal in green, and the quantization error is represented as in red color. The staircase approximation is not identical to the original continuous signal. You can clearly see that. So the difference between the two represents an error. Now the point to be noted that as this is a noise, so we do not have any relation to represent these values of amplitude values of noise with respect to time. So we need to calculate the power of the noise with the help of some fundamental mathematical aspects of theory. So we know that noise power will be calculated as the expectation value, or you can say that mean square value. Right? So the difference between the input and output signal of the quantizer become the quantization error. So that is a quantization noise. Now if I am considering a mid-right or mid-right, whatever is the uniform quantizer, so its quantization value, or you can say the step size, is very much important, because so for this quantization I'm just going to previous slides. You can clearly see that this is the mid-rise. So if this is the step size delta, then this point will be delta by 2 plus, and this will be minus delta by 2. So you can clearly see that the quantization noise will always lie between minus delta by 2 to delta by 2, right? So at this point, as the quantization errors always lie between delta by 2 to minus delta by 2, so assuming that our quantization error is lying between minus delta by 2 to plus delta by 2, we have to calculate the noise power. So that means the mean square value, which is the quantization noise, let us suppose I am doing on this page. So quantization noise power, let us suppose this is the quantization noise power, it will be equal to the expectation square value, like for example it is QE square, right? So that will be, as E represents the mean value, so I am going to the mean value, which is 1 upon delta mean square. So square and then integration, that will be for ranges from minus delta by 2 to plus delta by 2, and after that QE square and DQE. This is the expansion of expectation with the help of mathematical aspects. So this is considerably, if you calculate this, you will get 1 upon delta QE cube QE to the power 3 divide by 3, and from minus delta by 2 to plus delta by 2. So that value will be equal to 1 upon delta, then after that delta to the power 3 divide by 3 will be the common term, 8 minus plus del cube by 8. So the value will be del cube by del square by 2 3 are 8 and 2 4 are 8 and 4 3 are 12. So del square by 12. So the quantization noise power for PCM, this is very important. Quantization noise power for PCM, it will be given by del square by 12. So assuming that error I have considered that it is lying between minus delta by 2 to plus delta by 2, either you are considering mid-rise or mid-ride. Now if your peak value of the signal, as you are having analog signal, and let us suppose the peak value is minus of MP, right? For example, this one is minus of MP and the negative plus of MP, and the negative value is minus of MP. Then if I have a step size of delta, then how many number of step sizes? Let us suppose these are L. Step sizes are L, that means these are the quantization levels. So you can clearly see that the total gap between negative to positive is twice of MP. Each step size is delta. So the total number of step size, that means if you are calculating L, that will be given by twice of MP divided by delta. So or you can also say that delta is equal to twice of MP divided by L. So if you are breaking your minimum to maximum gap with the help of L levels, then total step size will be calculated by dividing the gap by L. Now as I have already told you, let us suppose L will be represented by 2 to the power n number of bits. Like for example, if total number of L required n number of bits, like for example I will told you, let us suppose L is equal to 16, then how many number of bits are required? 4. How? 2 to the power 4. If 8 number of cell levels are there, then how many number of bits? Minimum required number of bits will be 3. That does not mean that n is equal to 4 is not valid for 8, right? But it means that as I have to reduce the bandwidth, so minimum required number of bits are 3 for 8. Point to be noted, right? So you can use more than 3 or more than 3 bits to represent 8 levels. So minimum is 3. Similarly for 16, minimum is 4. So L, if I have L number of levels, then required number of bits, let us suppose 2 to the power n. So it is clearly see that n will be equal to log base to L, right? So you can clearly put this value of L in this expression. So you will get step size in terms of number of bits, that will be twice of MP divided by 2 to the power n, right? So that will also be MP divided by 2 to the power n minus 1. You can also say that. I want to calculate the quantization noise power, which is QE square. This one is the quantization noise power. So that was del square by 12. In the previous slide I have already proved. So that will be equal to MP square, let us suppose this will be 4, I am using this formula, so that will be 4 of M, so that will be del square by 12. So M of P, you can clearly see that 1 upon 12 into MP square into 4, right, from this formula, divide by 2 to the power n to the whole square, right? So that will be 4 3s are 12, but that will be MP square divide by 3 into 2 to the power 2n, right? So this is the quantization noise power. So this is the quantization noise power, which is QE square equal to MP square divided by 3 into 2 to the power 2n. Now this is the very important term, so you have to memorize this, that quantization noise power for PCM will be given for PCM. So the quantization noise power for PCM is given by QE square equal to, that is actually the symbolical representation. This is not a QE square is always. So you can clearly see that you can also represent as sigma E if you want to represent this. I have represented as with the help of this greater than and less than symbol between QE square and so on. So signal power, if okay, then that means I have quantization noise power, right? Quantization noise power. I have quantization noise power, right? Now any system, or specifically digital system, can be paired with the help of the signal to noise ratio. Actually, signal to noise ratio tells about the quality of the modulation or methodology. So in this case, as quantization noise are the part of quantization process, so we have to calculate the signal to quantization ratio for the PCM. That means how much your signal is, or how much your signal can overcome the quantization. This is the ratio for which is defined for that purpose. So signal power, let us suppose that I am using like for example a single tone signal. So the power of the single tone signal, if let us suppose our signal is x of t, which is equal to MP, either you are considering cos of omega ct or sine of omega ct, but your power is given by any sine or cosine signal, and the power peak value square divided by 2. So this will always be fixed for any single tone sinusoidal signal, which is MP square by 2, right? I have also mentioned this here. So quantization noise power will be, I have already calculated this, so MP square divided by 3L square, right? Because n is equal to 2 to the power 2n or 2 to the power n, so n square means 2 to the power 2n. That's why here L square is represented, right? So SQNR, that means signal to quantized noise ratio, quantization noise ratio, will be 3L square by 2 by dividing these two terms. So MP square will be cancelled out by MP square, so it will be 3L square by 2. So that means signal to quantization noise ratio do not depend upon the peak value of the you can say it only depends upon the number of levels. Higher number of levels means higher signal to quantization ratio. If you are using number of levels, that means required number of levels are comparatively low, then signal to quantization noise will be high. The ratio of power, so I can also represent it in dB, so that will be 10 because these are the power, so 10 log base 10 3L square by divided by 2. So this is the equivalent value of this 3L square by 2 in terms of log. So SQNR will be finally represented for PCM, it will be approximately equal to 1.8 plus 6 of n. The PCM transmission path, which is the third major important section of the PCM. So in transmission path, regenerative repeaters, you can use regenerative repeaters which actually receive the signal and remove the noise from that signal, and again you can say a refabrication, right? Refurbish your signal, right? For regenerative repeaters, actually remove the noise and regenerate your transmitted signal. That is very helpful for the receiving process if long distance transmission has been actually occurred. So the block diagram of the transmission path has been already shown in figure. So that uses equalization, then timing synchronization circuitry, and the decision making devices are required. Now PCM receiver, this is the PCM receiver. You can use that regenerative circuit. is the part, and then after that decoder and reconstruction filter is used for PCM as a receiver. This reconstruction filter is nothing but low pass filter, point to be noted. This is a low pass filter. So final operation of the receiver is to recover the message signal. Pulses are passed through the decoder, which converts it into equivalent decimal value. Yes, because you are encoding at the transmitter side, so you have to decode with the same reversible process for the equivalent values of quantization, right? Quantization levels. The output of the decoder is then passed towards the reconstruction filter, which is a low pass filter having cutoff equal to the message bandwidth. So this is the actually demodulation block diagram of pulse code modulation. And this is the very important term, which is ISI. Once you transmit, actually you are using a gate pulses. Now what will happen when if you consider the spectrum of the gate pulse, then you will find that it will be from -infinity to +infinity, right? So point to be noted. Now what will happen when you pass this infinite bandwidth signal to the finite band of channel, right? For example, your channel, every frequency, right? This is not all, every channel in this universe ideally are not all pass channel. So it will definitely you can say attenuate a lot of frequencies. So once you pass this your signal, this gate pulse to this band pass channel, so it will definitely suppress this spectrum. So you after passing through this, you will only get like this one, which is the some part of the transmitted signal, right? So what will happen now, after the channel you are receiving a finite band of transmitted signal. Now equivalent to this finite band, if you reverse the process, you will get your pulse extended from -infinite to +infinite, but relatively very low voltage from -infinity to +infinity, right? Because this is a reversible process. So your pulse will extend and insert to the next consecutive pulse. For example, this is single pulse transmitted, let us suppose one, and after that let us suppose another one is transmitted. So what will happen when all these processes will be done for that same pulse, for the similar pulse, that let us suppose this is transmitted after some delay, then you will see that another pulse, and you can clearly see that there is an interference, right? So that's why this is called as ISI. So as the PCM channel are band limited, I have told you the received waveforms are distorted and they extend to the next time slot. That's why I'm saying next time slot. Extend it to the next time slot, which is the next time slot for the another pulse, for another sequence, right? So resulting in an error in the determination of the received bits, right? Resulting in error in the determination of the received bits. So this situation is same as the crosstalk in PAM. So in PCM, the adjacent time slots are symbols in code representation of a single quantized sample, and hence the term ISI is used for PCM. So basically ISI is the inter-symbol interference, that means two inter-symbols, right? Two different symbols. Inter-symbols mean different symbols. Here I have represented only single bit, but I am talking about in terms of symbol, which is a combination of more than one bits, right? So in that case, as the two different symbols are considered now, these are called as inter-symbol interference, because these two different symbols are just interfering with each other. So this is ISI for PCM. Now the most important aspect is the bandwidth of the PCM. So for a band limited signal having maximum frequency content, you clearly know that if maximum frequency is FM, then peak to peak potential difference, and you can already consider the peak to peak potential difference is twice of MP. The total number of steps required is L is equal to 2 to the power MP divided by L. Similarly, total number of encoding bits will be L is equal to 2 to the power N. Now minimum number of samples required for FM. Definitely with the help of sampling theorem, you can clearly identify the minimum required number of samples to recreate the signal, it will be twice of FM. No problem. The total number of sample values will be twice of FM, right? Total number of sample is twice of FM. The total number of bits required, let us suppose, so if you are using n number of sample, then L will be 2 to the power n. So your n is the number of bits that will be log of base 2 and L. So to send one sample, you are using n bits, right? To use, if you are transmitting one sample, that is one sample, one level representing, then it requires n number of bits. Like for example, if you are transmitting 0, 1, 2, 3, 4, 5, 6, 7, these are 8. Then for one sample, let us suppose this is 1 is the first sample, second is the second sample, let us suppose. So what is the equivalent binary? It will be 0, 1, 0. So 3 bits are required for one sample. In this situation, 3 bits are required to send these 8 levels. So 8 samples, right? So total required number, one sample required n bits, so 2 FM samples required n into 2 FM bits. So this is the minimum, point to be noted, minimum bit rate of PCM. It will be twice of n FM, point to be noted. So the minimum bandwidth required to send this message will be 2n FM, because bandwidth and bitrate are corresponding to each other. So let FPCM is the bandwidth. Now if FPCM is bandwidth and you are considering the sample values, right? So you have to also consider, let us suppose if this is the PCM, if this is the bandwidth, and if you are again sampling, the required sampling rate will be twice of FPCM. So you are comparing both sampling frequencies, right? So at twice of FPCM will always be greater than twice of n into FM. So the required bandwidth of the PCM will always be greater than or equal to n of FM, right? This is all about the minimum requirement. So thank you very much.